Deep beneath the surface of the Pacific Ocean, where sunlight surrenders to absolute crushing darkness, a pressure wave began its journey. It was the summer of 1997, and the waters off the southwestern coast of South America were acting as a conduit for an acoustic event of staggering proportions. This was not the gentle hum of shifting currents or the distant rumble of a tectonic plate grinding against its neighbor. It was a singular, massive acoustic emission, an ultra-low-frequency sound so powerful it would soon reverberate through the annals of marine science. Thousands of miles away, researchers at the United States National Oceanic and Atmospheric Administration, or NOAA, were monitoring the continuous feed of acoustic data streaming from the ocean floor. Their equipment registered the anomaly immediately. It lasted for roughly 1 minute, rising steadily in frequency, a distinct audio signature that stood out sharply against the background noise of the sea. They dubbed it the Bloop, a whimsical name that entirely belied the sheer, terrifying magnitude of the deep-sea signal. To understand how we captured this puzzling anomaly, we must look to the infrastructure of the Cold War. The hydrophones that detected the signal were part of the Sound Surveillance System, a sprawling underwater network originally designed by the United States Navy to track submarines. As geopolitical tensions eased, this vast array of highly sensitive underwater microphones was partially declassified, opening a pristine window into the ocean soundscape for civilian scientists investigating the natural world. These hydrophones are strategically positioned within the SOFAR channel, a horizontal layer of water in the ocean at which the speed of sound is at its minimum. Because sound waves bend toward regions of lower speed, this channel acts like an acoustic waveguide, trapping low-frequency sounds and allowing them to travel vast distances with very little loss of acoustic energy. It is a natural oceanic megaphone, and it was broadcasting the 1997 anomaly across the entire Pacific Basin. When scientists examined the spectrogram of the event, the visual representation of the acoustic data revealed an astonishing geographical footprint. The sound was not localized to a single sensor. It had been recorded by multiple autonomous hydrophones spaced over 5,000 kilometers apart. For a single sound source to be detected across such an immense expanse of water, its initial volume had to be astronomically loud, far exceeding the typical acoustic outputs of known oceanic events. Naturally, the initial phase of the scientific investigation turned toward biology. The profile of the sound, specifically its rapid variation in frequency over time, bore a striking resemblance to the vocalizations of marine mammals. Blue whales, the largest known animals to have ever existed on Earth, produce low-frequency moans that can travel for thousands of miles underwater. However, a comparative analysis quickly presented a formidable mathematical problem. The acoustic energy required to generate the bloop was calculated to be several times louder than the loudest recorded vocalization of a blue whale. If the source was indeed biological, it implied the existence of a creature of unimaginable proportions, something far larger than any animal known to science, lurking undetected in the abyssal depths. This hypothesis ignited a firestorm of public imagination, conjuring images of prehistoric leviathans and mythical monsters hiding in the dark. Yet marine biologists remained deeply skeptical of the giant animal hypothesis. The deep ocean is certainly vast and largely unexplored, but an organism capable of producing such immense acoustic energy would require a massive food source and would likely leave other biological markers or evidence of its existence. The lack of any corroborating physical evidence made the cryptid theory highly improbable, forcing researchers to pivot their investigation toward alternative, non-biological origins. If not biology, then geology seemed the most logical culprit. The Pacific Ocean is ringed by a hotbed of tectonic and volcanic activity. Underwater earthquakes, submarine volcanic eruptions, and massive landslides are common occurrences that release tremendous amounts of acoustic energy into the water column. Acousticians began meticulously comparing the spectral signature of the 1997 anomaly against the known profiles of these violent geological events. The comparisons yielded frustrating results. An earthquake typically produces a chaotic, broad-spectrum acoustic signature on a spectrogram, appearing as a sudden, sharp spike of noise that slowly tapers off. A volcanic eruption creates a sustained, rumbling hiss. The bloop, however, had a distinct sweeping frequency modulation. It rose smoothly in pitch, a characteristic that simply did not match the abrupt, mechanical fracturing of the Earth's crust or the explosive release of magma. For years, the origin of the sound remained a profound puzzle. The anomaly sat in the NOAA archives, a tantalizing mystery that defied easy categorization. It became a textbook example of an unexplained natural phenomenon, a reminder of the limits of our understanding of the deep-sea environment. But the scientific process is fundamentally driven by patience and the continuous accumulation of new, seemingly unrelated data. The turning point in tracing the source of the anomaly did not come from re-examining the old data, but from expanding the acoustic net entirely. In the early 2000s, NOAA researchers deployed a new array of autonomous hydrophones much further south, positioning them in the hostile, freezing waters of the Southern Ocean surrounding Antarctica. The primary goal was to monitor ambient ocean noise and study the acoustic behavior of baleen whales in this remote, icy region. As the new hydrophones recorded the soundscape of the Southern Ocean over several years, researchers began to notice a recurring acoustic pattern. They were picking up massive, low-frequency sounds that bore an uncanny resemblance to the legendary 1997 signal. These newly recorded sounds had the exact same sweeping frequency modulation, the same immense volume, and the same remarkable ability to travel vast distances through the deep water channels. The crucial difference in this new phase of the investigation was that these southern sounds could be triangulated and correlated with visible physical events on the surface. By cross-referencing the acoustic data with satellite imagery of the Antarctic coastline, researchers made a definitive connection. The sounds were occurring precisely at the moments and locations where massive ice shelves were undergoing catastrophic structural failures. The mystery was finally unraveling, pointing not to a biological behemoth, but to a phenomenon known as an icequake. When a massive iceberg calves from an ice shelf, or when a large grounded iceberg fractures and scrapes against the rocky ocean floor, it releases an astonishing amount of kinetic energy. The cracking, shearing, and grinding of millions of tons of ice generate powerful ultra-low-frequency acoustic waves that plunge into the ocean depths. The specific frequency sweep of the bloop, the very characteristic that had initially mimicked a biological vocalization, was identified as the acoustic signature of ice tearing apart and vibrating as it fractured. When acousticians sped up the recordings of these Antarctic icequakes, they matched the profile of the 1997 anomaly perfectly. The puzzle was solved. The loudest sound ever recorded in the ocean was the sound of iceberg fracturing. This resolution fundamentally shifted our understanding of the deep ocean soundscape. It demonstrated that the cryosphere, the frozen water part of the Earth system, is a dominant contributor to the ambient noise of the global ocean. The acoustic energy generated by ice in the extreme southern and northern latitudes can travel across entire hemispheres, dominating the acoustic environment thousands of miles away from the original source of the fracture. Beyond solving a captivating mystery, this scientific investigation yielded a powerful new tool for environmental monitoring. By understanding the acoustic signature of icequakes, researchers can now use hydrophone networks to track the disintegration of ice shelves in real time. In an era of rapid climate change, where the stability of polar ice is of critical global concern, listening to the ocean has become just as important as observing it from satellites in space. The journey from an unexplained anomaly to a verified natural phenomenon perfectly encapsulates the rigor of the scientific method. It requires resisting the allure of sensational explanations and instead relying on the methodical collection of evidence, the formulation of testable hypotheses, and the willingness to let new data guide the conclusion. The initial biological theories, while fascinating to the public, were ultimately discarded when the acoustic data pointed toward a more grounded geological reality. We explore these anomalies not just to catalog the bizarre, but to expand the boundaries of human knowledge. The 1997 acoustic event challenged our assumptions about what was possible in the natural world. It forced researchers to develop better monitoring techniques, and to look at the ocean as an interconnected, dynamic system, where an event in the frozen south can echo all the way across the equator. While the bloop has been definitively identified, the vast, dark expanse of the global ocean remains a frontier of profound mystery. Countless other unidentified sounds, strange geological formations, and undiscovered biological entities still await their moment of scientific resolution. The hydrophones continue to listen, capturing the endless complex symphony of the deep, reminding us that every answered question in science only opens the door to deeper, more complex inquiries.